Dear students, Assalamu alaikum and welcome back to plant physiology course. In the previous video, we discussed various components of water potential. And now we are going to build on that and take it one step further. We are going to take an example to illustrate the relationship of these osmotic quantities or components of water potential. So we have a beaker here. This beaker contains a solution and we are going to name it solution A. So this is solution A. This beaker contains solution A, and as far as its water potential is concerned, we are going to mention its magnitude. So water potential is equal to minus 10 bar. For the time being, we are going to use bar as the pressure unit instead of Pascal or megapascal. Then we are going to place another solution inside this beaker, and this solution is contained in an inelastic membrane. So here is another solution, and this is contained in a container which has inelastic semi-permeable membrane. So this one is solution B, inelastic and semi-permeable. This solution B has a water potential of minus 30 bar. One thing that needs attention here, that we have mentioned the water potential of both the solutions, minus 30 bars in case of solution B and minus 10 bars in case of solution A. What about their solute potential or psi S? Because these are two solutions. We are talking about two solutions. One is in the beaker, it is open, and other is confined in a semi-permeable but inelastic membrane that does not allow increase in the volume of the solution if water enters through this membrane or when osmosis takes place. Now we are talking about these two solutions, especially their water potentials. This is before the start of the experiment, that is when these solutions were prepared, and now we are going to start the experiment. In this case, if we quickly take a look at the equation, in fact the equation is just right in front of us, and that is psi W water potential is equal to solute potential plus pressure potential, psi P. Now psi P is absent in this case because we do not see any pressure in any of these two solutions, and we are going to talk about this pressure momentarily. For the time being, since there is no pressure, there is no pressure potential, none of the solution has been subjected to any pressure, and psi P is 0. When psi P is equal to 0, that means water potential is equal to solute potential, or vice versa, that is solute potential will be equal to. So at this particular moment, when we are just starting the experiment, the water potential or the solute potential, they have the same values. That is, if the water potential is minus 30, then the solute potential is also minus 30. So in case of both these solutions, the solute potential is minus 30 as well, just like the water potential. So both of them have the same value. Before going further, let's talk about the psi P or the pressure potential, something about pressure potential. Now pressure potential is actual pressure or positive pressure it develops, especially when the solution is confined, and the confined solution is subjected to osmosis. Now again, we take the example of a solution. Now it is a confined solution containing a solution, whatever the water potential might be, say it is minus 20 bars. This is a confined solution, but there is no pressure developing inside because osmosis is not taking place. Now if this particular solution contained in a semi-permeable and inelastic membrane, so this is the semi-permeable membrane just like we have seen above, and we place it in a beaker, say of pure water. So far there is no psi p, or psi p is equal to 0, so it's psi w, which is equal to minus 20, is equal to psi s, which is its solute potential. So the water potential and the solute potential are the same. Now this particular solution is placed in this particular beaker with pure water, in which psi w is equal to 0, maximum free energy or chemical potential. So what will happen, that water will start moving in. Since this is an inelastic membrane, it will not allow the movement of water inside, and as water enters, a pressure will develop inside this particular solution, which is confined by an inelastic and semi-permeable membrane, and will reach at equilibrium, because as water moves inside, the pressure develops, that is psi p, and this particular psi p, it counters this water potential or the solute potential, whatever you call it. And what we get now, that on the outside we have water potential of 0, and here we have solute potential psi s plus psi p. So 0 is equal to minus 20, with a plus 20 pressure will develop, and we will get 0. So water potential on both sides will become equal, as the net movement of water molecule inside and outside this particular container will be the same. So this is a pressure potential which develops when a solution is confined and then subjected to osmosis, separated by, in most cases obviously, a hypotonic solution or pure water. So pressure will develop inside it, and that pressure counters the solute potential, and what we get, that the water potential on both sides, that is the solution outside and the solution inside, the water potential of both becomes equal. In this case it will become 0. So this was just to illustrate the concept of pressure potential. Now back to our experiment. Just to recap, as we know, we have two solutions, one which is in this particular container, and it has a water potential of minus 30 bars, and other solution which is in the beaker, and it has a water potential of minus 10 bars. The solute potential in both these solutions is equal to water potential, because there is no pressure potential, as osmosis has not yet started. Let's draw a graph to represent these values, and it will make our life much easier as we proceed and try to explain the relationship of these osmotic quantities. So here we have, let's take a different pen. Now this is 0 water potential, and this is our x-axis. So this is below 0, we have minus 10, minus 20 and minus 30 bars, and above 0 we have positive pressure, so we have plus 10, plus 20 and plus 30. Now let's represent these two solutions with boxes. So situation will be something like this. So we have solution A with a water potential of minus 10 bars, as you can see, and a solution B with a water potential of, let's use a different color, so it has a water potential of, so this is B. So we have solution A and solution B, one with a water potential of minus 10 bar and B with a water potential of minus 30 bars. Now next is their solute potential. So solute potential for solution A is also minus 10 bars, and that for solution B is also minus 30. So as you can see, we have minus 30 bars in solution B and minus 10 bar in solution A. Now both of these osmotic quantities have the same values. Here's the graph and overall position at the start of the experiment. We haven't yet started, and as you can see, this part, this is the water potential of both the solutions, solution A as well as solution B. So this row, this is for solution A, and this row, this is for solution B, as you can see. And then this particular column and the graph, they show the solute potential of both the solution A and solution B. And the final part, as you can see, it is absent in the graph because we are just starting the experiment. We haven't yet started, so there is no pressure. Pressure will build up only when water enters the solution B. So the pressure potential at the start of the experiment is 0, and obviously it has not been represented in the graph as well because its value is 0. We cannot show it because 0 is along the x-axis, so we cannot represent it. Now as the experiment proceeds, so let's draw that diagram again. So the same beaker having a water potential of minus 10 bars, and we have placed a container in it. Now what's happening now, that water will enter from solution A to solution B. Now this is B and this is A, and this is its solution level. Now this solution A will enter into solution B because solution A has a water potential or solute potential of minus 10 bars, and it has minus 30 bars. So this is solution B is hypertonic with respect to solution A, and solution A is hypotonic with respect to solution B. So what will happen, that water will enter the solution B from solution A. In other words, the chemical potential of water is greater in solution A as compared to solution B, the water potential, and water always follows the chemical potential gradient, and the direction of the gradient is from A to B. The tonicity, which determines the direction of osmosis from solution A to solution B. Since solution B is covered by an inelastic membrane which is semi-permeable and inelastic. It is semi-permeable, so it allows the movement of water molecules, but it is inelastic as it does not allow the expansion of this container B. So as water enters the solution B, what happens, that pressure builds up, and this is very common in our daily life. when we try to inflate the tires of our vehicles, whether it's a bike or a car or whatever it might be. When it is inflated, pressure develops inside it. Since this is already full of water and surrounded by an inelastic membrane, just as water enters or the experiment starts, the pressure builds up inside the solution B and we get equilibrium. Equilibrium is reached by entry of a very small amount or a negligible amount of water, because it does not dilute the solution B. So what we get? Equilibrium. Now what does equilibrium mean? It means that the water potential on both the sides, they are same. Now outside we know the water potential is minus 10 bars and inside it is 30 bars. Now equilibrium means that water potential on both sides is equal to minus 10. Now how it can be? Now this is how it's working. Now we have minus 10 in the beaker and inside we have minus 30 water potential or solute potential. So this is psi s, because water potential is equal to solute potential plus pressure potential. Now what happens, that a pressure potential of plus 20 bars develops inside this particular container, which is container B. In this container it develops a pressure of 20 bars, and this 20 bars is positive pressure. So by solving the equation, what we get, that minus 10 is equal to minus 10. The solution on the water potential of both the sides will become equal. Now it does not affect the solute potential. It doesn't change because the amount of solute in both the solutions is the same. What has happened, that due to development of this positive pressure, this turgor pressure or pressure potential, it has raised the water potential inside this container B. And what has happened, that the water potential has become equal on both the sides. So let's represent it by a graph. I'll just pause the video and draw it and then come back. The water potential of solution B, it has raised because of the entry of the water and development of the turgor pressure, and we are going to represent it something like this. So now its situation is somewhat like this. So this is A and B, their water potentials. Next is their solute potential, and obviously there is no change in the solute potentials. So this is solution A and this is solution B. Solute potential is same as it was before, 30. And next is the pressure potential. So we have A and B. As far as A is concerned, solution A, since it is unconfined, there is no pressure development. But in solution B, its pressure potential has raised, and now we can see it very clearly. And this is increase, so it is 20 bars. And this pressure potential, what has happened because of this pressure potential, that it has raised the water potential of solution B, not the solute potential. And now let's draw the graph below it, the table. Since we are drawing it below the first diagram, our previous diagram was here. This is the upper row is solution A and the lower row is of solution B, and the values are in bars. So we are going to draw this table. So right now we are going to draw the table. So we have 3 columns. This is column number 1, column number 2, and then the column number 3, and we have 3 rows. The upper row is for the symbols. So we have 1 and 2 and 3 columns. So this is psi W, this is psi S, and this is psi P, the pressure potential. The upper row is for solution A and the lower row is for solution B. So this is solution A and this is solution B. So solution A was minus 10, and the water potential of solution B has also become minus 10, whereas their solute potentials, they remain unchanged, minus 30 and minus 30. And of solution A there is no pressure potential, but in solution B we have developed a pressure potential of 20 bars. So as you can see from this diagram, that is, when osmosis started, the situation has become somewhat different, and as you can see, the effect on water potential and effect on the pressure potential. This is because of the development of pressure inside. The solute potential has remained unchanged of both the solutions, but the pressure potential has developed in solution B, and due to this pressure, its water potential is now equal to the water potential of solution A. We are almost done. Let's represent the entire process through an equation. So let's draw two tables. Now let's write down the equation. So this is psi W is equal to psi S plus psi P, and the same equation goes for solution B. So we have psi W is equal to psi S plus psi P. Let's enter the values. So in solution A, water potential is minus 10, and solute potential is also minus 10 bars, whereas pressure potential is 0. As far as solution B is concerned, water potential is minus 30 and solute potential is also minus 30, whereas the pressure potential is 0. This was the situation at the start of the experiment. So what we get, minus 10, and on this side minus 30. Solution B and solution A, they are both water potential as well as the solute potentials have the same values. And now the final state, again we have water potential is equal to solute potential plus pressure potential. So this is for solution A, and water potential is equal to solute potential plus pressure potential. Now let's substitute the values. So as far as solution A is concerned, the situation is unchanged. So we have minus 10 bars water potential is equal to minus 10 bars solute potential and no pressure potential. However, as far as the solution B is concerned, now at equilibrium the situation has changed. So we have minus 10 bars water potential, solute potential doesn't change, so it is 30, and now the pressure potential has developed and it is plus 20 bars, so it is plus 20. And now solving the equation, we get that minus 10 on one side is equal to minus 10 on the other side, because minus 30 plus 20, it will make minus 10. So at equilibrium, the water potentials of both the solutions, solution A as well as solution B, will be the same. After observing the whole experiment from start to finish, from start to equilibrium, we have seen that finally at equilibrium the water potentials of both the solutions are same. So here we make the general statement that when two solutions of different water potentials separated by a membrane that is permeable only to water molecules, then the water potentials on either side of the membrane will tend to equilibrate. So this is general statement. Both the water potentials on either side, the water potentials of the solutions on either side of the membrane, they will tend to equilibrate. So this was relationship of osmotic quantities. In the next video we are going to take a look at the same problem when we have different solutions of different osmotic quantities, osmotic potentials and water potentials, and how they are related. We are going to elaborate it more in the next video. Thanks for watching and see you in the next video.